Now onwards, we will talk about various instruments that are available for measurements of pressure process variables such as pressure, temperature, flow, liquid level, etc. And we will start our discussion with pressure measuring instruments. Pressure is a very important process variable. Pressure is defined as force per unit area. So, pressure is force divided by area. Force can be represented as pound force, kilogram force, Newton, dyne, etc. Similarly, area can be represented in terms of square inches, square feet, square centimeters, square meters, etc. Common units of pressure include pounds per square inch, also called PSI, Newton per meter square, which is SI unit of pressure. Newton per meter square is also known as Pascal. Symbol for Pascal is Pa. We can also use kilopascals. So, 1 kilopascal is 1000 pascals. Other units that can also be used for pressures are inches of water or inches of mercury, millimeter of water or millimeter of mercury, bar, atmosphere. 1 atmosphere is 760 millimeter of mercury. We also express low pressure in the unit of torr, where 1 torr is 1 millimeter of mercury. So, let us be familiar with, we should be familiar with these units: pounds per square inch of PSI, Newton per meter square or Pascal, which is SI unit, kilopascals, etc. Also, inches or millimeter of mercury or water, bar, atmosphere, torr, etc. We have seen during our discussion on instrumentation and process control that 3 to 15 psi is a common pressure range. So, let us remember 3 psi is approximately 21 kilopascals and 15 psi is 105 kilopascals. So, like 3 to 15 psi is a common pressure range in process instrumentation and control. The range translates to 21 to 105 in kilopascal unit. We should also remember 1 Pascal is equal to 1 Newton per meter square, which is nothing but 1 kg meter per second square, which is same as 10 dynes per centimeter square. We may also remember 1 atmospheric pressure is equal to 1.01325 bars, which is equal to 75.97 centimeter of mercury, which we ordinarily say 76 centimeter of mercury or 760 millimeter of mercury, which is equivalent to 29.92 inches of mercury, which is same as 10322 kg per meter square. So, this gives us the relationship between one unit to another. So, you can easily convert from one unit to another. Let us now define gauge pressure, absolute pressure, atmospheric pressure. Pressure above atmosphere is called gauge pressure or positive gauge pressure. We denote it by PSIG. Similarly, pressure below atmosphere is negative gauge pressure, also known as vacuum. On the other hand, absolute pressure is measured from a perfect vacuum. Let us look at this diagram. Let us take this as 0 absolute reference and this as atmospheric pressure. This is the pressure axis, and there is another pressure indicated here which is above atmospheric pressure. So, this excess pressure, excess with respect to the atmospheric pressure, is positive gauge pressure, whereas with respect to 0 or absolute reference, this pressure is total or absolute pressure. Similarly, if we consider another pressure level which is below atmospheric pressure, with respect to atmospheric pressure, this pressure will be termed negative gauge pressure or vacuum. While this pressure, the same pressure with respect to absolute 0 will be absolute pressure. Similarly, the atmospheric pressure with respect to absolute 0 reference will be called barometric pressure. So, pressure above atmosphere is positive gauge pressure, pressure below atmosphere is negative gauge pressure or vacuum, and absolute pressure is measured from a perfect vacuum or absolute 0 reference. We may note that differential pressure has no reference to either absolute vacuum or atmospheric pressure. So, differential pressure has no reference to either absolute vacuum or atmospheric pressure. Let us now classify the pressure measuring instruments that we frequently encounter with for measurement of pressure. We can broadly classify the pressure measuring instruments under 3 different categories depending on what is the magnitude of pressure we are measuring. We can measure a moderate pressure, we can measure a very high pressure, or we may be interested in measuring very low pressure or high vacuum. There are various instruments available for measurements of moderate pressures, and you can classify them as follows. We have manometers, we have various types of manometers, we have mechanical displacement type pressure measuring instruments such as ring balance manometer or bell type manometers. Ring balance manometer, bell type manometers can also be clubbed under manometers. Then an important class of pressure measuring instruments is elastic pressure transducer, where we have Boron tube pressure gauge, diaphragm type pressure gauge, and bellows gauges. We also have various electrical pressure transducers such as resistance type pressure transducer, potentiometer devices, inductive type transducer, capacitive type transducer, piezoelectric pressure transducer, and so on and so forth. So, you have various manometers, various elastic pressure transducers such as Boron tubes, diaphragm types, bellows gauges, and various electrical pressure transducers for measurement of moderate pressures. For measurement of very high pressure, normally electric gauges based on resistance change of manganese or gold chrome wire is used. On the other hand, when we need to measure very low pressure or very high vacuum, we have McLeod gauge, thermal conductivity gauge, also called Pirani gauge, ionization gauge, and Knudsen gauge. So, now we will see some of these, we will see in some more details of some of these pressure measuring instruments. This is an indicative range of various pressure measuring instruments. It is just an indicative range. Below 1 millimeter of mercury, we use manometers and low pressure gauges. Between 1 millimeter of mercury to 1000 atmosphere, we can use elastic pressure transducers such as Boron tubes, diaphragm gauges, and bellows gauges. For high vacuum, that is up to 10 to the power minus 9 torr or 10 to the power minus 9 millimeter of mercury, we use McLeod gauge, thermal conductivity gauge, ionization gauge, etc. And for very high pressure measurement, very high in the sense of 1000 atmosphere and above, we use electrical resistance type. So, by moderate pressure, we mean up to 1000 atmosphere. Very high pressure normally refer to 1000 atmosphere and above, and high vacuum may be 1 millimeter of mercury to as low as 10 to the power minus 9 millimeter of mercury, where we need to use special instruments such as thermal conductivity gauge, ionization gauge, etc. So, let us start with manometers. Manometer is one of the oldest means of pressure measurement. You are all familiar with at least U-tube manometer, which is shown here. So, it is an U-tube, may be made of glass, ordinarily made of glass, and inside the tube we have a fluid known as manometer fluid. Frequently mercury and water is used. Now, when these two limbs are connected to same pressure source, that means if P1 is equal to P2, the level of the manometer fluid in both the limbs will be same. But if P1 and P2 are connected to two different pressure sources, then there will be a difference in level of the manometer fluid in both the limbs. For example, this limb is connected to pressure source P2, this limb is connected to pressure source P1 and P2 is greater than P1. So, the manometer fluid is pushed down here and rises up here. So, H is the difference between the level of the manometer fluid in these two limbs. So, H is the output of this manometer, and this H is a measure of differential pressure P2 minus P1, because P2 minus P1 is rho times H, where rho is the density of this manometer fluid. So, by measuring this H, we can easily calculate the differential pressure P2 minus P1 if we know the density of the manometer fluid. While choosing manometer fluid for a particular application, we need to remember that the manometer fluid should not wet the wall, it should not absorb the gas, it should not react chemically with the fluid whose pressure we are interested in measuring, it should have a very low vapor pressure, and it should also move freely. Mercury is one of the most commonly used manometer fluid, as it satisfies these conditions well. So, it is important to note that manometer fluid should not wet the wall, it should not absorb or react chemically, it should have a very low vapor pressure, and it must move freely. So, this is how we can measure differential pressure with an U-tube manometer. Remember that manometers can be used to measure gauge pressure, differential pressure as well as absolute pressure. We can have various types of manometers. As shown in this figures, we have U-tube manometer, which we just discussed. We can have well type or reservoir manometer, which is shown by this figure. We can also have an inclined manometer, where one of the leg is inclined, and you can also have a float type manometer, which is essentially a modified version of well type or reservoir manometer. So, the various types of manometers can be U-tube manometers, well type or reservoir manometer, inclined manometer and float type manometers. Let us now look at more closely a well type manometer. In a well type manometer, one leg is replaced by a large diameter well. If you remember the U-tube manometer, this would have been like this, but this leg has been replaced by a large diameter well. Since the cross sectional area of the well is much larger than the cross sectional area of the other leg, when the pressure is applied to the well, the manometer liquid in the well lowers only slightly compared to the liquid rise in the other leg. So, let me repeat. In a well type manometer, one leg of the U-tube manometer is replaced by a large diameter well. Now, the cross sectional area of the well is much larger than the cross sectional area of the other leg. So, if we now apply pressure to the well, since its cross sectional area is much larger, the manometer liquid in the well will lower only slightly, but there will be a significant liquid rise in the other leg. As a result of this, the pressure difference can be indicated only by the height of the liquid column in the single leg. In case of U-tube manometer, we have to read the difference of the liquid level in both the limbs, but here we have made one leg large. So, the liquid lowers only slightly here and the liquid rises substantially in the other leg, which has much smaller diameter. So, effectively the pressure difference can be indicated by the liquid rise in the single leg. If this is connected to pressure source P1 and the well is connected to pressure source P2 and P2 is greater than P1, higher pressure is applied to the well. So, P2 is greater than P1, then it can be shown that for static balance P2 minus P1 is equal to rho, which is density of the manometer liquid, into 1 plus A1 divided by A2 into H, where A1 is the area of the smaller diameter leg and A2 is the cross sectional area of the well. So, for static balance we can write P2 minus P1 equal to density of the manometer liquid into 1 plus A1 by A2 into H. Now, since the cross sectional area of the well is much larger, A2 is much greater than A1. In other words, A1 by A2 is much less than 1, such that 1 plus A1 by A2 can be approximated as 1. So, P2 minus P1 is equal to rho times H. So, the pressure difference can be measured by the height of the liquid column in the single leg. That means, the leg with much smaller diameter. In fact, if the area of the well is 500 or more times larger than the area of the vertical leg, the error involved in neglecting the area term is so small that it can be safely neglected. You can see from the figure that from the schematic that the liquid lowers only by this much in the well, but the liquid rise in the other lake is huge. Let us now look at inclined tube manometer. In case of inclined tube manometer, one leg of the U tube manometer is inclined. The inclined leg expands the scale of the manometer such that lower pressure differentials can be read very easily. Imagine we are using an U tube manometer to measure pressure differential between P2 and P1, where P2 and P1 are not widely different. That means we are measuring a low pressure differential. Under this circumstance, the H, that is the difference of liquid level in both the limbs, will be very small. In fact, depending on the pressure differential, it can be so small such that it becomes extremely difficult to read. So, to overcome this, what we can do is we can incline one of the legs of the U tube manometer. So, that way the mercury will travel a longer distance along the inclined leg. So, by inclining one leg of the manometer, we can expand the scale of the manometer such that lower pressure differentials can be read easily. For example, if you look at this figure, this is the 0 line. So, if this leg was not inclined, but if this leg was vertical, the pressure differential would have been the small amount Rm. But by inclining it, the equivalent portion of Rm is R1, which is much easier to read. So, essentially we increase the sensitivity of the manometer. If the angle of inclination is alpha, we can show that for static balance, P2 minus P1 is equal to rho, which is density of the manometer liquid, into 1 plus A1 by A2 times R1 sin alpha, where R1 is this distance, which is essentially the output from the U tube, from the inclined tube manometer. Again, if A1 by A2 is much smaller than 1, because if I use an OLA here with much larger diameter corresponding to the diameter of the inclined leg, we can neglect A1 by A2. In that case, P2 minus P1 will be equal to rho times R1 sin alpha. The scale of the manometer can be extended greatly by decreasing the angle of the inclined leg alpha to a small value. So, we can increase the scale of the manometer by decreasing the angle of the inclined leg. Let us now look at float type manometer. This is a variation of well type manometer. We have a well with much larger diameter, and we have another tube, another leg whose diameter is less than this. These two, this well and this leg is connected by a flexible connection. And this well diameter is large enough such that you can put a float inside. Now, this is connected to the high pressure source, this is connected to the low pressure source. Now, as the manometer liquid changes its position, the float inside the well also changes its position, and the position of the float can be taken as a measure of pressure. We can choose a large float such that it generates enough force to move a pointer against a scale. So, the scale can be calibrated in the units of pressure, and from the pointer and the scale the pressure can be indicated. By replacing the pointer by a pen and by replacing the scale by a chart, this float type manometer can be converted to a recording type manometer. It is also easy to change the span of the measurement by changing the diameter of this leg. So, this is frequently called range tube. Since these two are connected by a flexible connection, if I change the diameter of this leg, the span of the instrument can be easily changed. So, this is essentially a variation of well type manometer where we place a float in the well. If one end of the U-tube manometer is sealed, and the other end is connected to the pressure source, and this is vacuum, then the manometer is essentially measuring absolute pressure. You are all familiar with barometer, shown schematically by this figure. A mercury barometer has a glass tube closed at one end with an open mercury filled reservoir at the base. So, what we do is we take a glass tube closed at one end, fill it completely with mercury, invert it and place it in a mercury filled reservoir. Mercury in the tube will adjust itself until the weight of the mercury column balances the atmospheric force exerted on the reservoir. So, atmospheric air is acting pressure on the reservoir. So, the mercury in the tube will adjust itself until the weight of this mercury column inside the tube balances the atmospheric force exerted on the reservoir. When the air pressure is 1 atmosphere, the height of mercury column will normally be 760 millimeter at 68 degree Fahrenheit or 20 degree Celsius. The top of the column will be vacuum. It will essentially contain saturated mercury vapor at the local temperature. But since the vapor pressure of mercury is extremely low and can be neglected safely, this is essentially vacuum. Now, let us move on to elastic pressure transducers, and we start our discussion with Boron tubes. Boron tube was first patented by E. Bourdon in France in 1849. So, it is a very old instrument. Boron tube finds wide range of application where consistent, inexpensive measurement of static pressures are required. There are various types of Boron tubes. C-type or C-shaped Boron tube is one of the most commonly used Boron tube. The figure shown here is a C-shaped Boron tube. The C-shaped Boron tube has a hollow elliptical cross section. So, this tube is hollow and elliptical cross section. It is closed at one end and the fluid whose pressure we are going to measure is applied at the other end. This end is also rigidly fixed. So, to make a Boron tube, we start with a tube with circular cross section, then flatten the tube to make the cross section elliptical, seal one end of the tube and bend the tube in the form of C. The fluid whose pressure I am going to measure is applied here, and this is rigidly fixed. A pointer is connected to the sealed end of the tube through a gear and linkage system. Now, when pressure is applied at the end which is rigidly fixed, the cross section of the Boron tube tries to become circular. So, you have Boron tube with elliptical cross section. When the pressure is applied here, the cross section of the Boron tube tries to become circular from elliptical one. This will cause the tube to straighten out until the force of the fluid pressure is balanced by the elastic resistance of the tube material. So, when pressure is applied inside the Boron tube, the cross section of the Boron tube tries to become circular, and this causes the tube to straighten out until the force of the fluid pressure is balanced by the elastic resistance of the tube material. Since the open end of the Boron tube is fixed, the changes in the pressure will move the closed end. A pointer is attached to the closed end of the tube through a linkage, gear and pinion assembly, and this will rotate the pointer around a graduated scale. We can have a graduated scale here. So, when the fluid pressure is being applied inside the Boron tube, the Boron tube will try to straighten out as this cross section tries to become circular, and this will cause the sealed end of the Boron tube move. So, the sealed end of the Boron tube will move as I apply pressure inside the Boron tube, and this movement or this movement of the tip of the Boron tube is a measure of the pressure. The tip movement can be indicated by connecting a pointer to the tip of the boron tube through this gear, link, sector and pinion assembly. We have talked about displacement measuring transducers such as LVDT, potentiometer, capacitive type, etc. previously. So, the deflection of the tip of the boron tube can also be measured by a displacement transducer such as LVDT, potentiometer and capacitive type, etc. So, the key point is that when I apply pressure inside the boron tube, there will be deflection of the tip of the boron tube which is sealed, and this tip deflection is the direct measure of the pressure being applied. The deflection of the tip of the boron tube is proportional to the pressure being applied. In fact, the tip deflection depends on various other factors. For example, for a particular design, the tip deflection can be expressed by this equation, which relates the deflection of the boron tube to k times theta times p times alpha times r to the power 0.2 divided by e beta to the power 0.33 to t to the power 0.6. What it means is the deflection of the boron tube depends on theta, which is angular length, this length, angular length. It depends on pressure being applied, directly proportional to pressure being applied, and the angular length. Depends on the radius of curvature to which the boron tube has been bent. Depends on geometry of the cross section. It is elliptical one, so it has a major axis and minor axis. So, tip deflection depends on major axis and minor axis. Tip deflection depends on the modulus of elasticity of the material that has been used for making the boron tube. The tip deflection also depends on the thickness of the boron tube. Deflection of the tip of the boron tube is inversely proportional to the modulus of elasticity of the material as well as thickness of the boron tube. A typical C-type boron tube may have a radius of 25 millimeter, may have a maximum displacement travel of 4 millimeter. Error in measurement may be 1% full scale deflection. Typical range is 0.1 megapascal to 700 megapascal, and the materials used for making boron tubes are normally those materials which has very good elastic property, such as bronze, beryllium copper, steel, alloy steel and nickel span C alloy. Nickel span C alloy is an interesting alloy whose modulus of elasticity does not change with change in temperature. For an appreciable change in temperature, the modulus of elasticity of nickel span C alloy does not change. Now, to increase the sensitivity of the Boron tubes, the Boron tube elements can be extended into spirals or helical coils. This increases their effective angular length. Remember, from the previous equation, we have seen that the deflection of the tip of the Boron tube is directly proportional to the angular length. So, more the angular length, higher the deflection of the Boron tube. So, to increase the sensitivity of the Boron tube, we can increase the angular length, and one way to increase the angular length is to extend the Boron tube element into spirals or helical coils. This will increase the effective angular length and therefore increases the moment of the tip of the Boron tube. Thus, it increases the sensitivity and resolution of the Boron tube. So, both the spiral or helical or double helix will increase the sensitivity of the Boron tube. So, for the if I apply the same amount of pressure in C type Boron tube and if I apply the same amount of pressure in spiral or helical Boron tube, the tip deflection in case of spiral or helical Boron tube will be much higher than that of C type Boron tube. However, this increased measurement performance is gained at the expense of a substantial increase in manufacturing difficulty and cost compared with C type Boron tubes. And this also decreases the maximum pressure that can be measured. In other words, the range of the instrument is decreased. So, increase the sensitivity of the Boron tube by using spiral or helical Boron element, but the cost of the instrument increases because of manufacturing difficulty, and at the same time we decrease the range of the instrument. So, the maximum pressure that can be measured with C type Boron tube is much higher than compared to spiral type or helical type Boron tube. Helical and spiral types can measure a maximum pressure up to 700 bar. So, once again C type Boron tube, spiral type Boron tube and helical type Boron tube. We can also use a double helix where a single helix is used to make another helix. We can also measure differential pressure with help of a Boron tube. We need to use two Boron tubes for that. Two Boron tubes are connected with one pointer in such a way that the Boron tubes indicate the pressure difference. Let us look at this. let us say we have a boron tube, we have another boron tube, the tip of the boron tubes are connected such that these two tips move in opposite direction such that the deflection of this pointer against the scale is a measure of P1 minus P2 or P2 minus P1. So, this way we can measure differential pressure with help of two boron tubes. Usually, air is used to calibrate a boron tube during manufacture, and the pointer of the boron tube is normally set at 0 when no pressure is applied to the boron tube pressure gauge. Now, if a different fluid, particularly a liquid, is later used with a boron tube, the fluid in the tube will cause a non-zero deflection according to its weight compared with air, resulting in an error of up to 6%. Usually, air is used to calibrate the boron tube during manufacture, and the pointer of the boron tube will be set at 0 when no pressure is applied to the gauge. Now, if I apply a different fluid, and the problem is worse if you use a liquid, a non-zero deflection we may get, and this will result in an error of up to 6%. This can be avoided by calibrating the boron tube with the fluid to be measured. So, instead of using air during the manufacturing step, we can use the fluid that we will finally use to calibrate the boron tube. Alternatively, we can also apply a correction factor However, if air is trapped in the tube, this will prevent the tube being filled completely by the fluid, and the solution proposed by both the methods will be difficult . However, if air is trapped in the tube, this will prevent the tube being filled completely by the fluid, and none of the solution will work properly.